Chapter 3, Moles Review. This is not the entire Chapter 3 in the Brown-LeMay book, but only that which is basic mole calculations for Unit 1. Okay, so these really are some of the same notes that we saw last year. You hopefully remember this slide. It just kind of goes over what is a mole, in that it's a way of counting particles. A mole of any substance we know is 6.02 times 10 to the 23rd particles. And those could be atoms, molecules, ions. Sometimes they call them formula units. It's really anything that we want to count as a mole in chemistry. Just like we would say a dozen is 12 things. A mole is Avogadro's number of things. It is counted particles in kind of an abstract way. Atomic mass, or AMU, sometimes it simply is marked with the U. I've seen that in some of the College Board videos. The mass of 1 mole of any element expressed in grams. Those values come from the periodic table, and so here we have a very basic comparison. 1 mole of hydrogen equals 1 gram. I think it's 1.01. And then 1 mole of zinc is 65 grams. Each of those samples would equal 6.02 times 10 to the 23rd atoms or particles of that substance. In sophomore chem, we rounded a lot to whole numbers, and that's perfectly fine to do for mental math on multiple choice problems. However, any free response problem, you want to keep at least 2 decimal places on your molar mass. So that's a new habit you're going to try to form this year on any calculations that you work freehand. Okay, this is your mole roadmap. You should have had this in your ISN last year. It's probably a good idea to go ahead and add it here in your ISN again, just so that you remind yourself of all of the conversions. So we have, remember, volume of gas we don't really touch on until we get to intermolecular forces in a gas law review. But we do molar mass for quite a lot of things, and particles for probably our share of things. So this is where we will spend the majority of the time here at the bottom of the table. And it's a good reminder that if you're going to the mole, you're always dividing by some value, whatever your conversion factor. So whether it's molar mass over here or it's particles over here, you're dividing by that value. And if you are trying to find the mass or the number of particles in a sample, you're going to be multiplying, because if you're starting with a mole, you're starting with small, and you're trying to find something bigger. Okay? So here's a couple of problems just to practice mental math on some molar mass problems. Remember that sulfur, if you have 1 atom, sorry, let me back up. So you're looking for the molar mass of SO3 here. And it says that sulfur, we see that sulfur is 1 in there and oxygen is 3 in there. So we look up each one's molar mass and we multiply that by how many atoms we have. And so 1 times 32 is 32 and 3 times 16 is 48. And you add those together and you get 80. So you would say that 1 mole of SO3, or sulfur trioxide, is 80 grams, which is also equivalent to 6.02 times 10 to the 23rd molecules of this compound. And then over here we have NH3. And so you have 1 nitrogen and 3 hydrogens. So 1 times 14 is 14. 3 times 1 is 3. Add them together, you get 17. So 1 mole of ammonia is 17 grams, or it is 6.02 times 10 to the 23rd molecules of ammonia. In the College Board video, there is a small error where she multiplies nitrogen and oxygen. I think it's in the oxygen where there's an error. Guys, it's not a big deal. Just, you know how to do the math. Sometimes in presenting these, we make little errors that we don't get edited sometimes. So not a big deal. Y'all should know that. We're going to try one on this page together. So here we have water, and everybody should know that water is, yes, 18 grams per mole, right? So we said we have hydrogen and oxygen. It's always important to list your elements. And you say, okay, I have 2 hydrogens times its mass of 1. Well, that gives me 2 grams. And oxygen, I have 1 times its mass of 16. So that gives me 16 grams. And I add it up, and lo and behold, I get 18 grams per mole. Same thing over here, calcium chloride. I have 1 calcium and 2 chlorine, so 1 and 2. Calcium has a mass of 40, so that's 40 grams. And chlorine has a mass of, I think it's 35.5 or 45, but normally we round it to 35, so it must be 45. So 35 times 2, we're going to say is 70, so 7 plus 4 is 11. So that's 110 grams per mole. Okay? Hopefully you got that. We're trying to make these quick. Calculate the molar mass for each of the following compounds. So pause the video, work those out, and I'll give you a minute to come back. Okay? So these are the masses we should have gotten for each one, give or take the rounding. So magnesium sulfate should come up with 120 grams per mole, and lead 2 chloride is 278 grams per mole. Okay, the next one we're going to do is a hydrate. It's been a little bit since we did a hydrate. It's kind of the same thing, but with a slight variation. So we did calcium chloride a couple slides ago, and we know that calcium, there's 1, chlorine, there's 2. Calcium has a mass of 40, so 40 times 1 is 40 grams. Chlorine, 2 times 35, we said was 70, so that gave us a mass of 110 grams per mole. But the water we treat separately. Every time we have a compound of water, we just write it, H2O, and we multiply it times, we know it's 18 grams per mole. So I didn't write a 2 there. So 2 times 18 is 36 grams. So then we add this 110 plus the 36 for its total mass. So 146 grams per mole. Take a minute, pause the video, work this other one, and we'll see how it came out. Okay. So going back, we knew that we had magnesium sulfate was 120.37 grams per mole. We add that to the 7 moles of water at 18 each is 126 for a total sum of 246.37. I hope that's what you got. Okay, our next process is using these molar mass to do some conversions. And again, we did these last year, so let's just fly through them. It says aluminum is often used for the structure of lightweight bicycle frames. How many grams of aluminum are in 3 moles of aluminum? So we always put our given, MOL, and it's aluminum. It's important that you write the compound, otherwise it doesn't have context. 3 moles of what? Okay. And then we're going to multiply this by our conversion factor. Since we have moles of aluminum here up top, we're going to cross it on the bottom so that it cancels out in a minute. And so I'm trying to find grams of that substance. So I'm going to the periodic table to see that 1 mole of aluminum is 27 grams. And then we're going to cancel out our units. So we have moles of aluminum and moles of aluminum that cancel. And so then 27 times 3, you should get 81 grams of aluminum. And in this one, it's not grams per mole because remember our moles canceled out. Okay, next one. Carbon dioxide is a byproduct of combustion. How many moles are in 88 grams? So again, that's given and we are looking for moles. So we're going to start with our 88 grams of CO2. And this time grams is up top, so we're going to put it on the bottom. And I'm looking for moles, so I'm going to have to put my mole up top. Every time you go to the periodic table, that mass is equal to 1 mole of the compound. So your grams should be offset with moles. So carbon is 12, oxygen is 16. Add that together, you get 44 grams. Again, your units cancel. This one's a beautiful mental math problem. 88 divided by 44, we see is just 2 moles of CO2. Next one, this one's a gas problem. It says a sample of neon has a volume of 44 liters at STP. STP is nice. We don't have to do PV and RT or any other fun things. We can do a straight stoic problem. And it wants to know moles of that compound. So you still put your given, 44.8 liters. We know that for every 1 mole of any gas at STP, there are 22.4 liters. All of this being neon. I missed that. Let me fix that. Neon, neon, neon. Okay, your liters of neon cancel out. 44.8 divided by 22.4 is a lovely 2 moles of neon. Okay, this one asks you, it says what volume would be occupied by 0.10 moles of helium gas at STP. And so we're going to be working with our moles and we want to find volume. So your given goes first, 0.10 moles of helium. And you know that for every 1 mole of any gas at STP, in this case helium, it is 22.4 liters of that gas. 0.10 times 22.4, you're really just moving the decimal place over 1. If you kind of unsure of that, probably ought to go back and watch our metric conversion stuff that we did at the beginning of the year. So moles cancel out. You're left with 2.24 liters of helium gas. Okay, this one says what volume at STP contains 20 grams of argon gas. So they gave us grams and they asked us for volume. So this is going to be a 2-step problem. So we're going to start with our 20 grams of argon. We have to first convert that to moles. So for 1 mole of argon, there are 40 grams of argon. That's its molar mass, 40 grams. So 20 divided by 40 is just 1/2 or 0.5 moles. And then we take that and we say, well, 0.5 moles of argon. And for every 1 mole of any gas at STP, that is 22.4 liters. And so 0.5 times 22.4, or half of 22.4, is 11.2 liters of argon. This one asks for atoms and it gives us grams. So again, it's a 2-step problem. So we're going to start and say, well, 32 grams of copper. And you have to first convert them to moles. So for every 1 mole of copper, there are roughly 64 grams of copper. And so 32 divided by 64, again, that's 1/2, so 0.5 moles of copper. And then you take your 0.5 moles of copper and you want to convert it to atoms. So we'll change pens. It says for every 1 mole of any atom, we know that there are 6.02 times 10 to the 23rd particles, in this case atoms. And it's okay to say atoms in this one without doing anything else because copper is a metal and any sample of that would be considered atoms. It's not a compound. So half, excuse me, of this number here, it's not going to change your exponent. You do 6.02 divided by 2, basically. And so 6 divided by 2 is 3.02, so you get 3.01. And my exponent does not change because dividing this front number by 2 didn't change a decimal place. So 10 to the 23rd atoms of copper. This question gives us molecules and it asks us to find grams. So again, it's another 2-step problem. So we're going to scoot this up just a little bit. We got room to work. And so you're going to take your 1.20 times 10 to the 23rd molecules of glucose. I'm not going to write it this time. It's a lot of room. And so we know that for every 1 mole of any compound, there are 6.02 times 10 to the 23rd molecules or atoms of that compound. And so you get this 10.23 cancels out because what you're doing is multiplying 1.20 times 10 to the 23rd times this 1 mole here. And so essentially this number and this number are on top of each other. So like 1.2 times 10 to the 23rd really is divided by 6.02 times 10 to the 23rd. And clean that up just real quick. Okay, and so the 10 to the 23rd is totally canceled. 1.2 divided by 6 is really like, if I move this over, we'd call it 12 divided by 6, and that would be 2. And then we'd have to take that 2 and move the decimal back over to account for that. And so your answer is 0.2 moles of glucose. Okay, and so then we're going to take our 0.2 moles of glucose as our new given, and we want to know that in grams. So we know that for every 1 mole of glucose, there are 352 grams of that. And again, you can kind of do 2 times that number. 2 times 35 is 70. So 2 times 352 is the same as if I was moving this over and I would put another decimal here in between the 5 and the 2. And so you get 70.4 grams of glucose as your final answer. Okay, our next one gives us grams of oxygen, and it asks us to find grams of calcium nitrate. So it seems a little bit tricky just by the reading. We see these every year in AP chemistry, and they always throw the students off a little bit. Don't let that get you. You are always going to take your given here, and you're going to convert to moles, and then you're going to find the next step. Do one step at a time, and do as much as you know. So this 24 grams of oxygen, this is not diatomic oxygen, it's within the compound. So we know that every 1 mole of oxygen is 16 grams of oxygen. So 24 divided by 16. Take a minute, put that in your calculator. You should be able to do it in our head. It's like 3 over 1. I don't know. Sometimes my brain doesn't work at night. So it's 1.5. 1.5 moles of oxygen. Okay, and so then that's our new given. But I want to know about calcium nitrate. So this 1.5 moles of oxygen, and we need a mole ratio. So for every 1 mole of oxygen, there is how many in this compound? So we have to come up here and look at this compound and say, well, there's 3 here, but there's 2 out here. So we're really multiplying. So 3 times 2 is 6. So there is, sorry, the 6 is going down here. There are 6 moles of oxygen in every 1 mole of this compound. Does that make sense? I hope. So kind of fixing that. Let me go back and do this. So we did the 2 times 3 in the compound to figure out that there were 6 moles of oxygen in 1 mole or 1 compound of calcium nitrate. Okay, so then you do the 1.5 divided by 6, and you get that there are 0.25 moles of calcium nitrate in that sample of 24 grams of oxygen. And then last but not least is to find the actual answer it asks for. How many grams of calcium nitrate is that? So we take the 0.25 moles and we multiply it times the molar mass of calcium nitrate. And it gives us that in the problem. So 1 mole of calcium nitrate is 164 grams of calcium nitrate. And so take a second with your calculator and do 0.25 times 164. And you get that that is 41 grams of calcium nitrate. Okay. This problem says how many grams of oxygen are contained in 14.2 grams of tetraphosphorus dicoxide. The molar mass is given. It's very similar to the last problem, but instead of working from the given of the element to the compound, you're working from the given of the compound to the element. But the problem really is kind of the same. So you're going to start with your given, that 14.2 grams of P4O10, and convert it to moles. Always and forever, go to moles first. So 1 mole of P4O10 is 284 grams. They gave it to us. We're good with that. So we're going to take our 14.2, divide it by 284, and we got 0.05. Sorry, I'm trying to move it a little bit. Moles of P4O10. But then we want to take that to oxygen, so we need to do a mole ratio to get from the compound to the oxygen. So 0.05 moles P4O10, and we know that for every one mole of compound, P4O10, there are 10 oxygens in that compound, right? 10 moles of oxygen. So you're going to take that number, multiply it times 10, and so you got 0.5 moles of oxygen. And then our problem actually asked us for grams, so we're going to have a new line that says 0.5 moles of oxygen. Well, for every 1 mole of oxygen, there are 16 grams of oxygen. So you do 0.5 times 16, and you find out that you have 8 lovely grams of oxygen in this compound. Okay, our next piece is percent composition. So we are taking the compounds that we have been looking at and we're breaking them into their pieces. And so this first one is just water, very familiar water, and you have to take each piece and figure out the molar mass of the piece and divide it by the whole. That's really all a percent is, the piece divided by the whole. So in water, we have 2 hydrogens. We have the molar mass of water. We have already found that it was 18 grams. So 2 divided by 18 is 1/9, which is like 11%. And then 16 is the mass of 1 oxygen. Well, 16 divided by 18 is like 8 divided by 9. And all we are doing to get this is to reduce these. Think like fraction reduction. You may or may not be able to make the leap from that fraction to the percent. It's okay. You can usually estimate from context clues with that much information. But your percentages should always equal 100. So 11 plus 89 does equal 100. We are good there. Okay, calcium chloride. I'm going to work this one together. So calcium chloride, we found out its total mass was 111 grams per mole. We want to figure out the piece of each one. So calcium is 40 grams. Should probably write what it is first. So calcium is 40 grams, and we're going to divide that by 111 grams. So it's a little less than 40%. I think it's like 37. Plug it in. Let's see. So 40 divided by 111 equals 36. So 0.36. We have to multiply that to get our percent. So we say that is 36%. It's usually okay to give whole numbers on percentages for something like this. And then chlorine has a mass of 35 each, but there's 2 of them there. So we'll say that's a total of 70 grams out of the 111 grams. We should expect that it would make up the difference, but 70 divided by 111 gives you 63%. And if I add those up, I really get 99%, and that's because we rounded a little, probably more than you would if this was a free response problem. But that's close enough, we're good. All right, empirical formulas is probably where we have the most problem, and it's been a lot of sleep since here, right? So it really is just the most reduced ratio of a compound. If you could take any, usually covalent compounds like carbons and oxygens and hydrogens, and you reduce them down by the lowest whole number ratio, that is what an empirical formula is. These are like our kind of rules for how do you find empirical formula. A lot of times you're given the mass or you're given percentages. So you're going to determine the mass in grams of each element, calculate that in moles. So if it's given to you in mass, great. If it's given to you in percentages, you're going to assume that those percentages are a mass. So that's where we get this little rhyme at the bottom, says percent to mass. Well, if you're given percent, you start there. If you're given mass, then you start here. Turn the mass into a mole, always and forever. This, divide by small, is what we're talking about. Calculate the moles and then figure out the smallest number of that whole number ratio. It has to be a whole number ratio. And then you're going to multiply until you get whole numbers. And we're going to do a couple of these for right now. But really, it's going to come back when we get a little bit heavier into stoichiometry later. Okay, this one here says, what is the empirical formula of a compound that contains 25.53% magnesium and 74.47% chlorine? AP would never ever give you this problem. One, it's mainly because it's an ionic compound, and you should know that magnesium has a 2+ charge and chlorine has a 1- charge, and we know that this compound will always be MgCl2. But let's pretend that we didn't know that for a minute, because we kind of forgot our chemistry over the summer anyways. So let's pretend that we don't know that. And we're going to work this like it was a covalent problem. Okay? So our first one says percent to mass. So we're going to pretend this 25.53 grams, or that our percent is grams of magnesium. And we're going to convert that mass to a mole. So for every 1 mole of magnesium, it's like 24 and some change grams. Okay? Divide, well, kind of wait, because we'll go ahead and do the other one. So then chlorine, we have 74.47%, but really that's grams of chlorine. And we know that for every 1 mole of chlorine, there is 35 grams per mole. So if we put these in the calculator, the magnesium 25.53 divided by 24 gives us 1.06 moles of magnesium. 74.47 divided by 35 gives us 2.13 moles of chlorine. So I'm going to rewrite that, moles, magnesium, and chlorine. So we have taken our percent to mass right here in the beginning. We just assumed that those percentages were grams. We're good to do that. Then we did our mass to mole. We took it and we converted them all to moles. Now comes for our next part. We're going to look at both of those, and the one that's smaller is the magnesium. So we're going to divide both of these by that number to try to get a ratio. So one of these should always equal 1. And so that makes our mole ratio pretty sound. So if I do 2.13 divided by 1.06, it's really close to 2. So you can see we have a 1-to-2 ratio, and that kind of proves our magnesium chloride that we know, which we usually get from our charges, which chlorine is 1-, magnesium is 2+. You crisscross those guys, and it's kind of a backup way of knowing that you got the right compound. When it's ionic, ionic works this way. We do this for covalent more often. Okay, so it says a sample of brown gas, a major air pollutant, is found to contain 2.34 grams of nitrogen and 5.34 grams of oxygen. Determine the empirical formula for the substance. I'd encourage you to pause this and come back and see how you did, but I'm going to go ahead and work it. Okay, hopefully you got at least this far. So we have our 2.34 grams of nitrogen. We divided that by the molar mass of nitrogen at 14 and got our 0.17 moles of nitrogen. We also took our 5.34 grams of oxygen divided by 16 grams of oxygen, its molar mass, and got 0.33 moles of oxygen. So now what we're going to do, we've done our percent to mass, which we really didn't have percent, so actually we can kind of cross that one out. But we did take our mass to moles. Remember that first step is not always necessary. Okay, the next step says to divide by the smallest. So we know that 0.17, 0.17 is smaller than 0.33. So we're going to divide both of them by the 0.17 so that we know we have 1 mole, or a ratio here of 1 mole of nitrogen for every, it's basically 2. So it's a 1-to-2 ratio of nitrogen to oxygen. We have whole numbers there. So our empirical formula is just NO2. May or may not be our actual chemical formula. We'll find out shortly. Okay, this one asks us to find the molecular formula of the compound we just finished. And it says it's a colorless liquid used in rocket engines, has a molecular mass of 92 grams per mole. What is the molecular, or sometimes called chemical, formula of this substance? So what we will do is figure out the molar mass of the NO2 empirical formula we had, and then compare that to the molar mass of the known compound. So just like before, we're going to write it out. We have nitrogen and oxygen. 1 nitrogen times 14 grams gives us 14 grams. And then oxygen, we have 2 of those, times 16 grams gives us 32 grams. And so 4, 5, 6, and 3, 4. We have a molar mass of 46 grams per mole of NO2. Well, we know that the true molecular compound is 92.0 grams per mole. So what we want to do is see how many times bigger that is than the one we just calculated. So 92.0 divided by 46.0 is roughly 2. I think it's exactly 2. So what happens is that we take that 2 and we multiply by our subscripts in the compound. So we get N2O4 is the actual compound for the rocket engines. Okay, we're going to do one more problem here. This is combustion. It's if you don't remember, a classification of elements and compounds. Combustion is just when we take a hydrocarbon, like this guy here. Could be carbon and hydrogen. Sometimes it's CH3, sometimes it's propane, butane. It could just be anything really with carbon and hydrogen. It's going to react in the presence of oxygen. Your products here are always carbon dioxide and water. And what AP does is they will give you the amount of CO2 produced or the amount of water collected, and they will ask you to work backwards to figure out this hydrocarbon that we started with. So this will be your goal to kind of puzzle backwards. And we did some of these in sophomore chem last year. We're going to do one of them. I'm pretty sure we did it in class. And again, you will see more like this when we do stoichiometry later. But for now, it'll jog your memory. So here we go. Okay, so this problem says a 27-gram sample of an unknown hydrocarbon was burned in excess of oxygen. There's always excess oxygen. I don't think I've ever seen a problem where you had to calculate the oxygen. But it does give us our products. We have 88 grams of CO2 made and 27 grams of water made. What is a possible molecular formula of the hydrocarbon? So we're just I think, going to have to find our empirical formula. This was our starting compound, our starting amount. I don't even know if we need that, so we're just going to kind of work it raw together. Here we go. Maybe it'll move up for me. Okay, so we have 88 grams of CO2. Hopefully at this point you know what step comes next. We're going to take it to moles. So I have 1 mole of CO2, and hopefully you remember that's 44 grams in that molar mass of CO2. So 88 divided by 44, that's 2 moles of CO2. Well, my starting hydrocarbon does not have CO2 in it, so I have to take it a step further and calculate the amount of carbon in my starting compound. So this is a mole ratio. So for every 1 mole of CO2, there is 1 mole of carbon, which I know kind of sounds like silly because most of y'all can see that, but it's important to be thorough and to have calculations that back it up. So we know there's 2 moles of carbon. So we're going to come back over here and try to do the same thing for the water. So we have 27 grams of water, H2O. I left off my decimal on both those, but it's fine for now. So 1 mole of water is 18 grams of water. I'm going to have to do that in calculator. I'm so tired. 27 divided by 18. See, this is important why y'all get rest the night before the AP test so y'all aren't tired and your brains work. So 1.5 moles of water. Okay, but again, this is kind of why it's important. You have to get it to the moles of hydrogen for it to be useful. So for every 1 mole of water, there are 2 moles of hydrogen atoms, right? And so we're going to do 1.5 times 2, and that says, well, we have 3 moles of hydrogen. So when we look back at our problem and it says, what is a possible compound that this hydrocarbon could be? Well, just basic C2, because there's 2, right? And then H3. I have no idea what that is, but if you want to look it up, have fun. Guys, I really hope this was helpful. And if you have any questions, let me know. Have a great evening. Bye.